Teresa, and I'm in year 2 of Biomedical Engineering, and this is my medical electronic project. Today, I will briefly explain the heartbeat acquisition system, a biomedical signal processing system. It begins with a microphone sensor that detects mechanical vibrations from a stethoscope's acoustic output and converts them into a weak electrical signal, about 0.5 to 20 millivoltage. This signal is first amplified by a preamplifier to increase its voltage level while preserving quality. Next, it passes through an inverting amplifier where the gain can be adjusted. The amplified signal is then filtered by a 7-key second-order active low-pass filter which removes high-frequency noise and allows only heartbeat frequencies to pass through for clearer analysis. After filtering, the signal enters an audio amplifier with gain control, which further amplifies it to drive a speaker. Finally, the speaker outputs the heartbeat sound clearly, and the system's gain control allows users to adjust the volume to their preference. This system is widely used for monitoring, diagnosis, and teaching purposes by capturing, processing, and outputting heartbeat sounds effectively. I will now discuss the circuit configurations and functions stage by stage. In the first phase, we have the preamplifier, which is a low-noise JFET input dual operational amplifier. JFET stands for Junction Field Effect Transistor. It has fixed gain and is a closed-loop non-inverting amplifier. Using IC1A TL072, it supplies a voltage gain which is generally somewhere between 10 mV to 1 volt, but does not provide current. The op-amp amplifies weak audio signals, making tiny details audible, and the circuit can be designed to enhance or reduce specific parts of the sound through gain and filtering. The circuit must bring the signal from an electrical microphone up to a suitable level for the input. It's included here at the start of the signal processing circuit because its property include low power consumption, low noise, high input impedance, and amplification. Reasons for the high input impedance are helpful because they ensure minimal loading effect, preventing delay. The amplification will boost the microphone's weak signals picked up from the heartbeat and provide voltage gain, thus it is suitable. The microphone feeds the initial heartbeat weak signal into test point 0. Additionally, test point 0 will be our function generator input for this project. Firstly, it will pass through the coupling capacitor C1 at 10 microfarad, which will block out DC bias voltages and signals from the input. At TP1, we have voltage divider being applied, doing its role as a level shifter. Moving on, you will notice that a level shifter is almost always necessary. A voltage divider is needed because it is a method to get a fixed voltage supply. In this situation, it is 4.5 voltage, half of the voltage supply. I know that because I applied the voltage divider rule formula because the source is VCC, which is 9 volt, and the two resistors, R5 and R6 of 10k ohms each, are arranged side by side. The voltage between the two of them is fed into the positive terminal of the op-amp, which supplies it to work at a single supply mode. The single supply mode will cause the negative side of the waveform to be cut without a level shifter. The level shifter fixes the waveform distortion and prevents the negative part of the waveform from being clipped abruptly by moving the waveform upwards. This is before and after of applying a level shifter. Additionally, fixed voltage supply is helpful because it prevents damage to components. Now we will look at the active passband filter here. It is made of C2, C3, R2 and R3. Essentially, it is an active high pass and low pass being cascaded. It blocks low frequencies and high frequencies, allowing only the frequencies between the cutoff points to pass through, forming a passband. The formula of the voltage gain of this configuration is 1 plus the feedback resistor over the ground resistor. Formula of each frequency cutoff points for each active filter is 1 over 2 pi times resistance times capacitance. The capacitor C4 of 10 microfarad at the end of the output of the amplifier is to couple it to the next stage later on and also remove any DC signals, still letting only AC signals pass. Before we start looking into the results table for amplifier at stage 1, I will walk you through how I start for circuit testing. The DC supply voltage for testing should be 9 volts, so I connected the positive terminal and the negative terminal. I ensure that I set my DMM to measure DC voltage. I set the DC supply to independent mode and put the current horizontally to the left, and adjusted my voltage until the DMM showed that it is about 9 volts. Before we start using the oscilloscope, we need to troubleshoot the probes to avoid using faulty probes. So I connected it to the 1k Hz signal provider and grounded it to avoid any noisy signals. And I press auto to see if the waveform is accurate. It should be a perfect square 1000 Hz waveform like this if there's no issue with the probe. We set the amplitude to 200 mV peak to peak, sine wave, high impedance, and ensure that the output channel is selected. Frequency is the only thing that you can change in the function generator moving forward in this experiment. Subsequently, the function generator, power supply, and oscilloscopes are all being used and grounded properly. For the rest of the video, the function gen, power supply, and ground will not be changed. The only thing that moves will be the channel probes. Oscilloscope channel 1 probe is connected to TP1 and channel 2 probe is connected to TP2. At 1k Hz, there is an amplification of 200 mV to 3.12 volts. Now, the only thing that I will change is the frequency, which will be put at 200 Hz. The voltage output amplification is more drastic from 200 mV to 4.72 volts because the gain has increased. The gain at 200 Hz is higher than 1000 Hz because 200 Hz is comfortably within the bandpass filter's passband, while 1000 Hz is at the edge or outside. Bandwidth will be more well elaborated on later. Based on what I just demonstrated, I slowly changed the frequency one by one. The voltage input is testing point 1 and voltage output is testing point 2. I also calculated their absolute gain and gains in decibels. As you can see, as the frequency from the function generator increased, the gain also increased. I plotted down the values in the graph to find the actual bandwidth of stage 1. The highest gain recorded from stage 1 is at 100 Hz, the absolute gain being at 22.18 as compared to the calculated gain using the aforementioned formula, 23. It is very close, hence showing that the results is as per calculated. After frequency at 100 Hz, the gain starts to steadily drop. From the highest point of the graph, we minus 3 decibels to find the lower and higher frequency cutoff point needed to get the pass band frequency. But why do we minus 3 decibels as a cutoff frequency? We know that this is a formula to find the voltage gain in decibels, so if you put negative 3 decibels in the formula and perform some equation manipulation, divide both sides by 20, rearrange it, making the gain approximately 0.707, since power is proportional to the square of voltage. As seen as in this formula, the square of voltage gain will be the power gain, 0.5 or half. Mathematically, the negative 3 decibel point is where the output voltage is about 70.7% of the input, meaning the output power is half of the input power. This is why we define the cutoff frequency at negative 3 decibel to mark where significant attenuation begins, which is when power is halved. Now, let's compare the actual bandwidth with the calculated bandwidth. The bandwidth formula is simply just higher frequency cutoff minus lower frequency cutoff, making it frequency cutoff of the high pass filter minus the frequency cutoff of the low pass filter. This gives us the pass band of the band pass filter, which is 1048 Hz. That is close to the one that we found practically, which is 1383 Hz. This range of frequency is chosen because normal hard sounds are between 20 to 150 Hz and murmurs can go up to 1000 Hz. So by using the bandwidth estimated at 1383 Hz, we capture all important hard sounds while filtering out unwanted low and high frequency noise. Now on to stage 2, IC1B TL072 IC chip is being used. It shares the exact same IC chip in phase 1, just different pins. This inverting amplifier has a closed loop negative feedback. A portion of the voltage output is returned to the input. However, the output waveform will be 180 degrees out of phase or inverted as compared to the input. The level shifter is being implemented again by a voltage divider involving R9 and R10 at 10k ohms each. The fixed voltage is at 4.5 volts. The voltage divider must be connected to the positive to function as a level shifter, thus making this a single supply mode, so that leaves us with the inverting terminal. The trimmer is being used as a feedback resistor in the inverting amplifier configuration because it can be used to adjust the gain to not saturate the output voltage. The formula of the closed loop voltage gain is a negative feedback resistor over the input resistor, showing that the feedback resistor has a direct relationship to the gain, meaning the higher the resistance of the trimmer, the higher the gain, making the gain adjustable as well as the strength of the signal. The trimmer being put at the inverting terminal makes the signal mode more stable and has a better frequency response and also reduces distortion. In the process of stage 2, the waveform is inverted, but that has no practical effect. So further down the circuit, there is no need to invert it back. For audio output, our human ears cannot detect phase inversion and sound is still heard the same way, so it's not that important. Channel 1 probe is connected to testing point 2 and channel 2 probe is connected to testing point 3. The rest remains the same. To adjust your waveform for better viewing and comparison, always press auto once, adjust the waveform to be AC and adjust the width and height. Appropriate lengths should occupy 2 or 3 boxes. At 200 Hz, the voltage input versus output just shows a 180 degrees inversion from 4.8 volts to 6.32 volts. If I turn the trimmer anymore, it will be saturated and clipped. So this implies that 6.32 volts is the maximum amplification. At 1000 Hz, it has a 180 inversion as well. The gain of the result at different frequency differs, so the output here once again is lesser as compared to 200 Hz. By turning the trimmer, we can see how the feedback resistance affect the output waveform. It will be amplified and at some point it will get saturated and cut off, and that is the maximum. At this third stage, it is patched as an active Sallen-Key second order low pass filter with unity gain. IC2 is a second TL072 IC chip being used in this system. Coupling capacitor C5 at 10 microfarad connect the last phase to this phase and block out DC signals, letting through only AC signals. A voltage divider consisting of R11 and R12 of 10k ohms each acts as a single supply mode and also as a level shifter to prevent output from being clipped. So, a fixed voltage of 4.5 volts is being fed into the positive terminal of the active Sallen-Key second order low pass filter. It allows low frequencies to pass and rejects any high frequencies. We know that it's a low pass filter because the capacitor is shorted to the ground, and it's second order because it is made of 2 sets of RC networks. One set equals to 1 order of the filter. The voltage output is being fed back via C7 at 10 nanofarad and also directly shorted into the inverting terminal, meaning its gain is unity, equaling to 1. Unity gain makes it so that the V-in and V-out will have the same value. The coupling capacitor C8 10 microfarad will connect this stage to the next and filter out any DC signals, only letting through AC signals. The formula of the bandwidth in this low-pass filter is the higher frequency because the lowest frequency that it will let through is automatically 0 Hz, making the higher frequency the cut-off frequency and the bandwidth. The roll-off rate is negative 40 decibels per decade because it is a second-order filter. One order means negative 20 decibels per decade. This means that beyond the frequency cut-off point, the rate of attenuation and frequency, the filter starts to attenuate the signal amplitude. The further away from the cut-off, the weaker the output signal becomes for that frequency. This is the frequency cutoff formula, which is 1 over 2 pi square root of RA times RB times CA times CB, which can sometimes be reduced into 1 over 2 pi RC if the resistors and capacitors share the same value. But for this project, it does not, so we will be applying the original formula. Then we will find that the frequency cutoff is 996 Hz by calculation. Channel 1 probe is connected to testing point 3 and channel 2 probe is connected to testing point 4. The rest remains the same. Output at testing point 4 is being controlled by the input at testing point 3, so by adjusting the trimmer at stage 2 earlier, it can also control the output at testing point 4. At 200 Hz, the voltage output is at unity gain, being similar to the voltage input. In other words, it has a voltage gain of 1. At 1000 Hz, unity gain does not apply to the voltage input and output, and it will no longer be equal to each other. After 500 Hz, which will be explained later on, there is a drop in the voltage output. Thus, the final output will be the maximum sine wave attained without being saturated. So I changed the frequency respectively and filled up this table with the remaining calculations and measurements. Looking at this table, I can conclude that when the frequency is below 500 Hz, the filter is at unity gain. But any frequency more than 500 Hz, the gain and voltage output will start to drop. I drew out my frequency response curve and minus 3 decibels down and found that my cutoff frequency measured is about 800 Hz, which is pretty close to the calculated value. The low-pass filter in stage 3 is set to be around 996 Hz because it allows all useful heartbeat frequencies to pass through clearly while filtering out unwanted high-frequency noise. This cutoff is practical as it uses standard component values, ensures circuit stability, and maintains the clarity of the hard sounds without attenuation. C8 is a coupling capacitor again that connects this stage to the next, blocking DC signals and allowing only AC to pass. At stage 4, we have the audio amplifier or line-out gain control with internal single supply mode. It drives current to the speaker. The waveform from the previous stage will enter the last stage of the biomedical signal processing system via the potentiometer E terminal. You will notice upon further analysis that this is the only stage in this entire project that does not use a voltage divider as a level shifter. That is because IC3 LM386N-1 acts as a single supply mode internally. Being the last stage of the signal processing circuit, it is the only amplifier in the whole circuit to drive current to power up the speaker. The input will first go through the trimmer P2 with a maximum resistance of 100k ohms, where pin E has a full amplitude, while pin A and S has zero amplitude of the input waveform. The potentiometer is an adjustable 3-terminal variable resistor. As you rotate, the wiper moves along the resistive track, changing the resistance on either side. This makes the output voltage vary smoothly from 0 volts ground to the full amplitude. When the wiper is turned towards E, the input signal, the voltage signal at S will be equal to VE, the full amplitude. However, when the wiper is turned towards A, the grounded end, the voltage signal at S will be equal to 0 volts in amplitude. The trimmer can change the resistance or gain and act as a voltage divider. It also is our volume control, which helps allow the user to adjust to desired level of volume. Capacitor C15 50 mF filters out high frequency that is above 40k Hz. Without it, the output waveform will be slightly unstable. Basically, C15 divert high frequency signals to the ground, bypassing high frequency noise, while resistor R17 with 10k ohms limits current. Maintain a stable load and ensure that the capacitor doesn't act like a wire connecting output to ground, but instead forms a safe, useful, and high frequency load. I understand that after the output of op-amp at pin 5, this part before C13 looks a lot like a passive filter, but it is not. Upon further research, it is a Sobel network. The Sobel network is designed to stabilize load impedance, especially in an amplifier system where passive filters are designed to shape frequency response. The Sobel network is made of a resistor and a capacitor in series connected across a load, and its main purpose differs from a passive circuit. In this case, I can confirm that the Sobel network is being used because the load is the speaker at the end point. Capacitor C13 220 microfarad allows low AC signals to pass while blocking DC bias to send into the speaker. This ensures that the speaker outputs and the heartbeat sounds clearly with minimal loss. It is our final coupling capacitor that connects the entire signal processing circuit to the speaker. Channel 1 probe is connected to testing point 4 and channel 2 probe is connected to testing point 5, and the rest remain the same again. At 200 Hz, the voltage input is 1.22 volt and the voltage output right before saturation is 6.4 volt. At 1000 Hz, the voltage input is 560 millivolts and the voltage output right before saturation is 6.5 volts. We will get an output voltage of about 6 to 7 volts each time. By adjusting trimmer P2, we can control the voltage output at TP5. The final output will be the maximum sine wave attained without being saturated. At last, channel 1 probe is connected to testing point 1 and channel 2 probe is connected to testing point 5, and the rest remain the same. At the end of this test, we can see that the input voltage at stage 1 is still 200 millivolts peak to peak, while the output voltage at stage 4, testing point 5, is amplified to about 6 to 7 volts. This shows that the signal processing system works perfectly. As mentioned earlier, stage 2 leads to the signal being inverted amidst the signal processing, but this has no practical effects since phase inversion doesn't change how we hear sound, so there's no need to invert it back. This shows that the circuit has successfully amplified the weak input signal from the microphone to a strong enough output to drive the speaker. Overall, this confirms that each stage, the preamplifier, inverting amplifier, low-pass filter, and audio amplifier is working correctly to process and amplify the heartbeat signal for output, and so the signal processing system